Hi everybody. In the last lecture, we talked about elastic waves in a continuum solid. So when we say continuum solid, we basically mean that we disregard the fact that materials are made out of atoms and can be treated as a continuum. So under that assumption, we wrote down the wave equation for waves, elastic waves, sound waves going through our solid, and we also established certain relationships between the wave vector and the frequency, which is called as the dispersion relationship. And then we moved on to compute what are called density of states, and that actually allowed us to understand the contributions made by Einstein and Debye with respect to the specific heat of solids. So in this lecture, what we are going to do is to not disregard the fact that our solids are made out of atoms. So we are going to put in the atoms, and we are going to see how that affects our picture of the waves that go through our lattice, through our solid. And we are going to introduce the important concept of phonons. Phonons are nothing but quantized lattice waves, and the lattice waves by themselves are nothing but collective oscillation of the atoms of the solid. So essentially, phonons are quantized lattice waves, which basically means that if omega is the frequency of a phonon of a particular mode of vibration that goes through our solid, then the energy of that phonon occurs in multiples of h bar omega. This basically is what a phonon is, and we are going to get deeper into that today. Yeah, so to reiterate, a phonon is nothing but a quantized lattice wave, and if omega is the frequency of a phonon, its energy is in integer multiples of h bar omega. Now, Einstein and Debye actually already introduced this concept when treating the specific heat of solids. Now, although they introduced the concept of the quantization of the energy, uh, the lattice itself was not made explicitly discrete, right? So the lattice itself was considered as some kind of a continuum, but the energy of the lattice waves were quantized, right? So this is a subtle but important fact that I would like to make a note of. So let us very quickly recap what we have learned with respect to the dispersion relationship of a continuum situation. And we are going to very briefly and superficially identify what we expect would happen if this continuum picture was replaced by a discrete picture of our solid. Right, so that's what we're going to do right now. We're going to recap what we did in the last lecture. We're going to draw the omega versus q diagram and point out what we expect in the continuum picture and what we expect in the discrete picture. And then subsequently we are going to explain why this deviation really happens, right? So here is a dispersion relationship that we have actually seen before. This is the omega versus q behavior. The dashed line indicates the linear relationship between omega versus q, which we derived in the last lecture, and that is the continuum picture result. So omega equals the velocity of sound times q, the wave vector or the wave number. The solid line that you see is really what we expect. So this is this behavior, the solid line. You see that it deviates from the linear dashed line behavior, and that's the behavior we expect in the case of a discrete solid. So now let me pause for a moment and ask the question as to why we expect this type of a deviation. Why do we expect the discrete system to display a dispersion relationship that's different from the continuum picture, from what the continuum picture tells us, right? And note that this deviation occurs at large values of q, but not at small values of q. So the question is why? So I'm going to pause for a moment so you can think about this and come up with an answer. So there it is. The reason this happens is because q, which remember is equal to 2 pi over lambda the wavelength, cannot increase indefinitely, because at some large enough value of q, lambda may approach interatomic distances. So the wavelength of a wave that's going through our solid cannot be smaller than the interatomic distances, and so q has to have upper cutoff. And so when you approach such large values of q or small values of the wavelength, we expect the continuum picture to break down. And so this is really the fundamental reason behind this deviation that we just saw in this plot. Okay, let's see what we're going to do now. What we're going to do is consider a one-dimensional monatomic lattice, meaning we're going to consider a 1D lattice with equally spaced lattice points, lattice parameter A, and we're going to associate one atom per lattice point. So, which is why we're calling it as a monatomic lattice. So it's a 1D monatomic lattice. And then we're going to consider displacements of each of the atoms of this solid, of this 1D solid, and we are going to apply Newton's laws of motion, and we're going to come up with a relationship, with omega to q relationship. Actually, we're going to come up with something like a wave equation, very similar to what we saw with the elastic solid, and from there on we're going to derive a relationship between omega and q, and we're going to actually quantitatively show that the deviation that we see in this plot for a discrete system with respect to the continuum system can actually be derived. So that's actually the goal. So we're going to consider a 1D lattice, and for that 1D monatomic lattice, we are going to write down the dynamics of the equation that describes the dynamics of the atoms of our system, and that's going to be our entry point into understanding the deviation of this dispersion relationship. So there is our 1D monatomic lattice with lattice parameter A. The red atoms represent the atoms that have been clamped to the lattice points. There's one atom per lattice point, so which is why it's a monatomic lattice. And we are labeling the atoms using n, right? N minus 1, n, n plus 1. Those are the indices that label our lattice, label our atoms. And each atom is undergoing a displacement because of the wave that is going through this lattice, right? So we are representing the displacement by the letter u, as before when we discussed elastic waves. That's kind of what we did. So the displacement of atom n minus 1 is represented as u n minus 1. Displacement of atom n is u n. Atom n plus 1 is u n plus 1, and so forth. So note that at 0 Kelvin, we don't expect any displacements other than the 0-point motion. But at any non-zero finite temperature T, each of the atoms of this lattice is going to be displaced from its equilibrium position, and that's what we represent as U. So now what we're going to do is we are going to apply Newton's equations of motion to the atoms of this lattice. So we're going to consider a particular atom, let's say N, and we're going to apply Newton's equations of motion to that particular atom. Okay, so here is the Newton's equation of motion applied to our atom N. So the term on the left hand side is essentially the force on atom N, which is written as mass times acceleration, right? M, capital M, is the mass of each atom, and of course it's the mass of our atom n, and d squared un over dt squared is the acceleration. So you got m mass times acceleration on the left hand side, and on the right hand side we write down the restoring forces, right? You have our atom n, which is getting displaced. So this is our atom n that is getting displaced by un. But note that the interatomic distance between atom n and atom n plus 1 depends on the displacement of atom n plus 1 as well. So the net displacement between atom n and atom n plus 1 is given by un plus 1 minus un, and our alpha here is the spring constant, is a quantity that represents the spring constant between atom n and atom n plus 1. We are assuming nearest neighbor interactions only, and so alpha represents the spring constant between atom n and atom n plus 1. In fact, alpha is the same, the spring constant is the same quantity for any two neighboring atoms. Okay, so the first term on the right hand side represents the restoring force due to the interatomic distance due to the bonding between atom n and atom n plus 1, and likewise the second term represents the restoring force due to the displacement of n, atom n, and atom n minus 1. So you see, atom n has two neighbors, right? Atom n has neighbors on either sides, n plus 1 and n minus 1, and so the restoring force on that particular atom n is going to be controlled by what happens to n plus 1 and n minus 1, which is why you have these two terms on the right hand side. Okay, so we have defined a few terms here. M is the mass of each atom, alpha is the force constant or the spring constant, and we assume nearest neighbor interactions only, and we get this equation of motion for atom n, which we're going to simplify right now. We can just move things around and group terms, and we will get this equation. So this equation is actually quite similar to the elastic wave equation that we wrote down in the last lecture. Note that in that particular case we had a differential equation that involved a second derivative with respect to there was second order in time and second order in position as well, right? And we wrote down a general solution, and we impose boundary conditions and so forth. Now, if you look at this particular equation, you will actually notice that this is also a second order type differential equation, second order in time and second order in position, although the second order in position part may not be immediately obvious. Second order in time is obvious on the left hand side of this equation, right? You got d squared u over dt squared, and on the right hand side what you have as 2un minus un plus 1 minus un minus 1 is really a finite difference version of a second derivative. So it should not really come as a surprise that the general solution for this equation is almost identical to the one that we saw earlier for elastic waves. So in this general solution, xn, capital Xn, represents the equilibrium position of atom n, and this general solution basically tells us how that particular atom is going to jump up and down or left and right with respect to time. So all we are going to do now is to substitute this general solution into our wave equation right above, and we are going to derive the relationship between omega and q, the dispersion relationship, when we explicitly consider the discreteness of our crystal, of our solid. So that's our next step. So we're going to substitute this general solution into our wave equation, and let's see where that takes us. So here is the first step in the process. We just took the general solution, substituted into our wave equation, then we get this, and we can see that a number of terms can actually get cancelled out, such as this one here cancels that one, and of course the A cancels out. And let's move on to the next step now. So what we have done here is cancelled another term, which is e to the I, q, and a on both sides. Note that it occurs in all the terms of this first equation. And then after that, things get simplified considerably. And in the last step, we have just used a trigonometric relation to perform this algebraic operation over here. E to the iqa plus e to the minus iqa is nothing but 2 times cosine qa. Okay, so we have a series of steps. They're all basic algebraic steps. At the end, we have this equation over here, which basically gives us a relationship between omega and q. And a is, of course, the lattice constant of this 1D lattice. And omega m is a quantity, is a constant that is defined over here. So, this was our final result. This is the final result, important result that relates omega and q. Now, it's actually a simple matter to make a plot of omega versus q, and that's what we're going to do next. And that plot will allow us to compare this result with the result of the continuum picture that we have been discussing earlier. So let's take a look. Let's take a look at how this omega versus q plot looks like. So this is the answer. So here is the omega versus q plot. The dashed lines that are inclined at a certain angle, that's our continuum result. So this is what I'm talking about. That's our continuum result. And the solid lines are, of course, the results given by this equation over here. So you can actually make a lot of interesting observations. First of all, at low values of q, with small values of q, the continuum result and the new result are identical. When you reach values of pi over a for q, right, the continuum result is different from what we are seeing over here with this equation. So there is this deviation at those values of q. Another thing that you will notice is that there is some kind of a periodicity. Remember, this is a sine function, and of course it's going to be periodic. And so you see that this kind of a repetition occurs. And the periodic unit, of course, is 2 pi over a, and because you can center it over here, you can actually define the unique region of this omega versus q plot as going between minus pi over a to plus pi over a. And you may recall that in one of the previous discussions we noted that this is what we call as a Brevon zone for a one-dimensional lattice with lattice parameter a. So what we are going to do now is write down and make a note of a series of observations that relate to this plot and this type of a dispersion relationship, omega versus q. So the first observation we make is something we have already made, is that as q tends to 0, we are approaching what is called as a long wavelength limit. We have discussed this in the previous lecture. So as q tends to 0, when we approach the long wavelength limit, our omega is equal to omega m times a divided by 2 times q. All we have actually done is go back to this equation and we set omega q tending to 0. When q becomes very small, sine qa over 2 is the same as qa over 2, and then from here we get this equation. What we see here is that omega is now linearly related to q, and with this being the proportionality constant. So we are recovering the continuum picture at small values of q, or when wavelength is very large. So that's our first observation. Let us now make another interesting observation. make some room for myself. So this equation also implies that the velocity of sound, recall that the velocity of sound is this term. So the velocity of sound then has to be equal to omega ma divided by 2. And when we discussed elastic waves, we wrote down this expression for the velocity of sound, square root of the Young's modulus divided by the density. So if this equation were to be true, then this quantity here has to equal to that quantity over there. And remember that we just defined omega m to be equal to square root of 4 alpha over m. Remember, alpha is the spring constant or the force constant, and m is the mass of our atom. If you just work out the algebra, basically you'll see that this equality here implies this. So our spring constant is equal to the lattice parameter times the Young's modulus of the material. So that's a useful relationship. Before we move on to the next point, let me make one observation. Let me pictorially try to explain what we mean by the long wavelength limit. So the long wavelength limit essentially implies that the wavelength is much bigger than the interatomic distances, and when that is the case, something like this picture is what will be happening. So the distance between two atoms is your lattice parameter A, and your wavelength is actually this whole distance over here, which is much bigger than A. And these little arrows are intended to show the displacement of these atoms. You see, this atom is clamped, is not moving. Likewise, this atom is not moving. So these are the two end atoms which are not moving. This is slightly moving, and so is this. This is moving a little bit more, and so is this. And this is moving a lot more, and so is this. And so this pattern of displacement implies that the wavelength of this wave is long. So this is a pictorial representation of what we mean by the long wavelength mode. Okay, so now let me move on to another important point. And this point deals with what happens as q tends to pi over a. Remember that as q tends to pi over a, the wavelength tends to 2a, because q is equal to 2 pi over lambda. So the question is, what is going on when q tends to pi over a? Remember, when q tends to pi over a is when you see the maximum deviation from the continuum picture. So that's what we're going to explore next. So here is what happens. So as q tends to pi over a, lambda tends to 2a. And if you notice carefully, this plot that we showed earlier, let's go back. So when q tends to pi over a, you see the slope of the omega versus q curve is 0. Remember, the slope of this curve is the velocity, is the wave velocity, or to be precise, it's called the group velocity. So as q tends to pi over a, the group velocity tends to 0. What is going on? What is going on here is essentially Bragg scattering. And we are going to try to visualize this pictorially again. And of course, before we do that, let's make the observation that when d omega over dq tends to 0, when it equals to 0, the group velocity equals 0, what we really have is a standing wave. And whenever we encounter standing waves under these situations, it is the signature of scattering, Bragg scattering. Okay, so let us pictorially visualize what is going on here. Okay, so here is a picture of what could be happening. So again, we have our 1D lattice, red atoms being our atoms clamped to the lattice points, and of course they are not clamped, they are jiggling around, they are moving around, and the arrows that you see represent the pattern of vibration. So this atom is going a little bit to the right, and this atom is going by the same amount to the left. And likewise, all other pairs of atoms are doing exactly the same thing. One set of atoms is going to the right by a certain distance, and the other set, the adjacent atoms, are going to the left by the same distance. So there is dynamics. Atoms are moving around. But if you now visualize the pattern of vibration, you will see that with respect to time, there is no wave that is going from left to right or right to left. In fact, you have a left going wave exactly cancelling the right going wave, and so the net result is that you have a standing wave. Atoms are moving, each individual atom is vibrating, but the overall picture, the collective motion of the atoms, results in a wave that is standing. And this is, as I said, a signature of Bragg scattering. So that's an interesting observation, and that occurs at Q equal to pi over A. And that, as I mentioned earlier, is a Brevon zone boundary. So at the Brevon zone boundaries in general, you can expect scattering and standing waves, right? So this is the physical meaning of what is going on at pi over A, Q equals pi over A. Okay, so now we are going to move on to yet another important observation, and this observation deals with the fact that our frequencies cannot keep rising indefinitely. There is an upper cutoff to the frequency of our phonons. Let's see what this is about. So this is a very important observation. Our 1D system can support only frequencies below omega m. Remember, we defined omega m earlier. Let us actually take a look at what we did define earlier. Let's go back a few slides. There it is, at the very top of this page. You see omega m defined, right? Move it down a little bit. Okay, so this omega m was actually defined for a purpose, right? So this is the maximum value our omega can actually possibly take. And let's now go back to what I had just written down. So the 1D lattice can support only frequencies below omega m. That's the upper cutoff, right? And omega m is defined earlier as square root of 4 alpha divided by m, which is 4ay divided by m. You can substitute typical values for a, y, and m, and you will find that this value of omega m is roughly of the order of 10 to the 13 hertz. If you think about it, this corresponds to the infrared regime. And if you also think a little more about it, you will realize that infrared and of course Raman spectroscopy are used to map out the vibrational density of states, densities of states of solids. And the reason infrared is used is because these are the typical frequencies of lattice vibrations. So it's a very important observation that the frequency has a maximum, has a limit. Above a certain cutoff frequency, no lattice modes, lattice vibrations are actually supported by the lattice. Okay, our next important observation is also something we have already made. It is that our omega versus q displays a periodicity. So omega as a function of q has a periodicity of 2 pi over a. The unique region is of course 0 to 2 pi over a, or an alternative way of defining this unique region is to say that q has to be between minus pi over a to plus pi over a, which appears to be the standard convention. And this region has a name which I've already mentioned. It's the first Brevon zone, or first BZ. So minus pi over a to plus pi over a is the first Brevon zone of our system. Now the question is, what is the physical meaning of this periodicity? How is it possible for two different values of q separated by 2 pi over a, because 2 pi over a is the periodicity, remember? So how is it possible for two different values of q separated by 2 pi over a to have the same frequency? What does this mean physically? So this is a point we will now explore, and it's not very difficult to understand how this curious behavior can come about. So here is a mathematical way of stating this puzzling behavior. So periodicity basically implies that the omega at q plus 2 pi over a is equal to the omega at q. So this basically means that waves with two different wavelengths, because remember q is equal to 2 pi over lambda. So this implies that waves with two different wavelengths are equivalent to each other and they have the same frequency. Right? How is this possible? What does this mean, and how can this be? So let us try to explain this again pictorially. Okay, so let us consider two waves with two different values of q's separated by 2 pi over a, right? So the two different values of q's are represented as q and q prime. So let's consider a first wave with a q equals pi over 2a. And then we're going to consider a second wave q prime um, with its q prime value being q plus 2 pi over a. Right? It's pi over 2a plus 2 pi over a. Now we are going to ask the question as to what the wavelengths of these two waves would be. Right? Let's just calculate that, and let's okay. So the wavelengths of these two waves would be 4a and 4a over 5. And you can work this out because q equals 2 pi over lambda. So now in the pictures below, I have attempted to show how it is possible for two waves, one with wavelength 4a and another one with wavelength 4a over 5, to actually be equivalent. Right? Let's take a look at the picture on the left. So we have a lattice containing these atoms periodically spaced with lattice parameter a, and this distance of course is 4a. There are four lattice spacings. So now we want to draw. What I've done here is to draw a wave with wavelength equals 4a, and you can see that this wave has a wavelength of 4a, and these atoms over these points over here indicate the actual displacement. It represents the displacement of those atoms. So this atom doesn't move. This atom is moved down. This atom is moved up, and so forth, such that the pattern of displacement is consistent with the wave that I have drawn with the wavelength of 4a. Now let's go and look at this picture on the right. Once again, the pattern of displacement of the atoms is the same. So this atom is displaced down here. This atom is still in that location. This atom has gone up. This atom is at its own position. This atom has gone down. So the pattern of atomic displacement in this picture is actually the same as that in this picture. However, now what I have done is I have attempted to draw a wave with wavelength 4a over 5, meaning in a 4a distance I have 5 wavelengths. You see, so the oscillation of the wave is actually very different here compared to that. But if you now compare it to the pattern of atomic vibration, they are actually the same. So this pattern of atomic vibration is equivalent to that. So physically, although the waves in the two cases are different, the pattern of atomic vibrations that underlie the wave motion are actually identical in the two cases. So it is possible for two waves with wavelengths with the wave vectors, wave numbers separated by 2 pi over a to actually correspond to the same physical situation. That is what I've attempted to explain over here. So okay, so I hope that clarifies this puzzling behavior. Now we are going to move on to a couple of other important points. One of them again relates to symmetry. Let me write this interesting feature. So this interesting feature relates to inversion symmetry. Now because the lattice is actually equivalent along the positive and the negative directions, this implies a similar symmetry for the reciprocal space as well, for the q space as well. And so omega q is equal to omega at minus q. So there is always going to be inversion symmetry. So the final observation after this that we are going to make relates to also another type of symmetry, and this has to do with periodic boundary conditions. What happens when we impose periodic boundary conditions on our system? This is something we have seen before when we dealt with elastic waves. And so something similar, we're going to see something very similar to that right now. Okay, so we're going to impose periodic boundary conditions. So we have been through periodic boundary conditions before, and PBC is the acronym we are using for periodic boundary conditions. And if we assume that our 1D solid can be represented as a system displaying periodic boundary conditions, and if we assume that the length of our bar, length of this little 1D solid to be L, capital L, the allowed values of Q are can be n times 2 pi over L, where n is an integer, positive, negative, or 0. When L is large, of course, Q becomes a continuum. And there is this little plot I've drawn on the left, omega versus Q plot, where you can see the deviation from the continuum behavior as Q approaches plus minus pi over A. And if you look carefully at the horizontal axis, of course, the range, the first Bravon zone range is minus pi over A to plus pi over A, but there are little divisions along the Q axis, and each little division is of length 2 pi over L, where L is a very large number, of course. Now, if you want to count the number of modes, how many patterns of vibration, how many wavelengths, how many modes that we can possibly have in this solid, that's a very easy calculation to make. Actually, we have done that before. So let's just write that down real quick. So here it is, the little derivation, right? The number of modes in our 1D solid is equal to the total number of points in the first Bravon zone, obviously. So those are the total number of allowed Q points, and those are the number of modes. And that you can calculate by taking the ratio 2 pi over A, that's the total length of the Bravon zone, divided by 2 pi over L, the distance between any two allowed Q points, and that gives you the number L over A. L is the length of the solid, A is a lattice parameter, so L over A is nothing but the number of atoms in the system. And this is also equal to the number of degrees of freedom of our 1D lattice, right? If you have n atoms in the system, the number of degrees of freedom in one dimension is n. So the number of modes is equal to the number of degrees of freedom at the end of the day. So this is an important point you want to bear in mind. So the number of modes is equal to the number of degrees of freedom. Not necessarily always equal to the number of atoms, right? Because in 3D, if you have n atoms, the number of degrees of freedom equals 3n. So the number of modes will be equal to the number of degrees of freedom. So that's an important final point I want to make. Actually, one other thought I want to leave you with is that any pattern of vibration in our solid is going to be a linear combination of these modes that we have just discussed. The question that we are going to explore in the next lecture is what happens when you have more than one atom associated with a lattice point. In other words, what if the basis is composed of more than one atom? So that will take us to a discussion of 1D diatomic lattices, and we'll see that there is something interesting that happens to our dispersion relationship, which is this. There is going to be a new feature that will get added to this dispersion relation when we go from one atom per lattice point to more than one atom per lattice point. More later. Bye-bye.